Well, I'm going to get rolling. So the topic of the talk today is strong device identities through SRAM PUF. I think probably the first part of it is pretty well understood. The second half of it might be a little bit fuzzy for some people. So I usually talk about things from a big picture first, give you the whole landscape, do all of that stuff. But I'm actually going to go down to the fine-grained stuff first, because you'll be thinking about that the whole time. So I'm just going to address that first, and then we'll talk about the landscape and how this works inside of the IoT space. So, quick corporate overview, SRAM PUF technology, the security landscape, and then time for Q&A. IntrinsicID, who are we? Privately funded startup company, spun out of Philips in 2008, headquarters in Sunnyvale, R&D team in Eindhoven. What we do, authentication. We're the world leading authentication company, especially when you focus in on the area of SRAM PUF. PUF is physical unclonable functions, and it's important to keep in mind that that SRAM comes before there, because that's what our technology is based on. There's a lot of PUF out there, a lot of conversations about it. We feel very strong about why we chose to run it on SRAM. I won't go into a lot of the details on that, but I will show you how we get to the point of authentication through using the characteristics of SRAM. So we're the #1 in patents, #1 in design wins, and #1 in deployed products for SRAM PUF technology. Scale, robustness, and the security of SRAM PUF has already been tested in multiple shipping products. We have the most experienced SRAM PUF engineering team. It was nice of the EU to give us last year the Innovation Radar Prize. What that means in essence is that out of technology that was coming out of Europe in 2016, we were the most exciting technology that they could see that had commercial viability. So not just that it was neat, there's a lot of neat technology out there, but the ability to actually then turn that into revenue. So that's what that award represents for us. Markets that we serve, Internet of Things, secure transactions, government, and defense. So, the big picture for us, our overarching goal and message, authenticate everything. Now, unfortunately, the word everything is used all over the place right now, but that's just the nature of IoT. It's the Internet of Things, right? They're all connected. So we're very, very passionate about the word everything, because we literally want to see every connected device out there have the ability to connect to a network and remain authentic, so that we can trust it, because there's a lot of scary things that are happening out there if you don't have trust all the way out to every individual end node. Because now we're transferring money, now we're sending personal information, now we're getting analytics and data and everything that's being collected from all these nodes. So if you look at these nodes, we take kind of some examples across the bottom there: smartwatches, cars, phones, mobile platforms, light bulbs, even all the way out to the aircraft. What's unique about each one of those? They're all built on a piece of silicon. So that's the core below there. They have an integrated circuit, a chip, something that's inside of there that is running their computational functions. And each one of them, this one is unique to that device. But if you just look at them across the board, this could be a similar chip in all of those. It could be the same from the same company. But what we can do with the SRAM PUF is that we can show that how each one of these are as individual, or even more individual, than people. Right, so they have their unique characteristics that we can drill down to and give it a unique identity. By getting to that point, we have device unique keys now that are on each one of these devices. With that device unique key, now you can start building up the other layers of security. You can move into verification certificates, okay, that says, here are your roles, and I've signed this, and somebody trusts me to give these roles and permissions to you, and I can verify that. Other layers that you start building up on some of these devices, confidentiality. So now I want to push down information onto you, and I want to securely store it on you. I'm still depending on your unique identity for the verification, and then also the confidence here. So now I'm DRM protection, things like that, where you move up the chain. So this, in essence, is what we are doing. The difference between what we do and what's already out there, because this may look very similar to everybody already. Like, yeah, there's keys on devices. I know that. They inject keys. They've been doing it for a long time. Sure, I've got verifications because CAs have been around forever. Sure, confidentiality, locked down on the device. Got that. The difference between what we do and what's currently happening out there, those keys right there, we never store them. So they are not stored on the device. So for the attack threats where you're going in and pulling these keys off of all of these devices to clone, duplicate, spoof, break into, legacy model leaves the key on there somewhere. And you can argue till you're blue in the face about how hard it is to get in to get that key. But the end result is those keys have been broken. Okay? We don't leave the key there, and that's the difference between what we do with our technology for that device unique key. So we'll dig into the SRAM PUF technology a little bit. This is very high level, quick walkthrough. What you have is process variation in the silicon manufacturing process, okay? So there's these variations that give each transistor slightly different and random electric properties. We focus our technology on SRAM. One, because of its prevalence, it's everywhere. Anywhere you have a computational device, you're gonna have something to store next to it. You're gonna have some memory. It also happens to be a very nice platform for a source of randomness for us. After years and years of studying lots of different places to get that randomness from. The other thing that's nice about using this SRAM is that we don't have to change it at all. We're not asking the silicon manufacturers to put a different block of SRAM in that has been modified by us. Use your existing SRAM. It's already there. So don't change your silicon. Don't modify things at the silicon manufacturing stage. We'll use what you already have. When those SRAMs come up, they either come up as a 1 or a 0. That's the basics of it. When you look across a 1K block of SRAM for us, you get a 100% random and repeatable pattern. That's the tricky part. So the entropy source is there, it's random. With our technology, we can get back to that exact same key every single time. And this has been done over millions of devices, over temperature ranges, over voltage ranges, over humidity, over time. And we can prove that we can continue to recreate that exact same key. So that fingerprint turns into this key that we've been talking about. So that's the cryptographic key that you can then use to build everything else above that in the security layers. Advantages of SRAM PUF: it's device unique, it's unclonable, it leverages the existing entropy source, and no key material is ever programmed on the device. This gives you a little bit of an idea about secure key storage, which is a little confusing because I've told you we don't store the key, right? But people still refer to it as, where's the key? It has to remain on there in some way. And so what we have is that we have our technology where it remains there, but only when it's active and needing to be used. It's not sitting there where somebody could look for it. Down here along the bottom, we talk about cost. Up here, we talk about security levels. Real quick, I'll just throw up other existing solutions that are out there right now. This is where we're talking about ROM-based fuses, EEPROM, anti-fuse. All of these kind of scale up in simplicity and to cost, and they also come up a little bit on the security level. But what happens with all of them is that there's a key programmed externally. So the key comes from somewhere else, has to find its way into here, and it requires permanent physical alteration of the device. If you've burned those fuses, it's permanent. That's the idea of it. It stays there. It's always there. Also, again, you could argue about the difficulty levels on all of these, but the end game is that key will be visible in the structure somehow, some way, depending on how important it is for you to get to it. Layer SRAM PUF on the top of it, keys generated by the device entropy, and no traces of sensitive data in there. So you can see on the cost scale down here, it's your existing SRAM that's already inside of your chip. We're not even asking you to add any more to it. Security level, because it is not leaving any trace of sensitive data, we feel it'll always lay on top of these existing solutions. let's take a little bit about layering security architectures for a microcontroller. Basic building blocks. Processing unit, CPU. A crypto module, if you're lucky, more and more that's going to be there. You've got some flash, you've got some SRAM. Maybe you don't even have that flash. So there's lots of ways to build up your security. The first thing you're going to do is you're going to generate a key, provision it, and store it. And right now the model says I'll do that with OTP. So I'll provision it during silicon manufacturing, or maybe I can push it out to distribution or into the contract manufacturing position. But at some point, I have to burn that key into that device. And again, it's generated externally. That means, again, from an attack vector, you've got this key on the outside that needs to get on the inside. And there's an intersection point there. And it's also the fact that it has to be then stored and secured. How do you secure it? Now I've got to add a memory protection unit into this, because now I'm going to store it in my flash. I'm going to rely on the OTP. I'm also potentially going to put another key in here, which means I've got to use this MPU to then block off some part of the memory. And again, there's lots of different ways to get to this, but this is a very general overview. So you've got device authentication and software boot chain verification, and then you've got the protection of your cryptographic keys. What happens if we add PUF? And remember, keep in mind, I'm adding PUF to this. I'm not even saying replace your OTP. Go ahead, use it. It's already existing, it's there, it's a model you're comfortable with. If you wanted to layer security on top of that, you can add a chip-unique SRAM PUF key that's unknown in the supply chain. So you might use this key for something, but this key, you know, will never be known in the supply chain. It's only known to the device itself. So the OEM can move this anywhere in the supply chain and have a tighter level of trust, a smaller trust perimeter that they have to work with, because the key never leaves the device. Talking about root of trust, there's less to no dependency on the MPU for this, because I'm not storing any sensitive data in the flash. If you took out that OTP, took out the MPU, you could still use this, because the key is only present when the SRAM is on and when it's needed. Nothing stored there that's sensitive. So we have two main product categories for our silicon keys. We have QuityKey, which is our hard IP. So this is delivered as an RTL. Typically, this is purchased by the silicon manufacturers, and they build it into their device. So what they have is they have a hard RTL block that's built into this MCU architecture. We also have a product called BroadKey. Now this gets very interesting because it's software IP that the device manufacturers can buy. Or the silicon manufacturers are even looking at this as a broader and quicker way to deploy SRAM PUF technology across their entire portfolio in one sweep, rather than waiting for tape out and tape out and tape out. So with BroadKey as a software IP, it's delivered as libraries, and very, very big difference here. This is a hard block. This is software that's running in Flash. And again, you get into the how do you protect that and everything. That gets into your secure boot and your method of how you're going to protect everything on your device. The SRAM PUF is still hardware. So BroadKey drills down to a hardware root to that SRAM and still gets the exact same silicon characteristics that QuityKey is doing. So even though we have to call it a software IP, because that's what it is, that's how it's delivered, it has a root hardware component to it, because we're always drilling down to that SRAM. So now, how do you put this out into the marketplace? How's BroadKey used? How's QuityKey used? And this just shows a new product that we just released here this week, and this is called Citadel. So what Citadel is, it takes that IP and then it wraps it around with manufacturing tools and then also OEM management suites. So that's the ability to manage the keys, their certificates, when they're out on devices in the manufacturing flow, also even out in the field for in-field provisioning. So if we take a real quick walk across this, QuityKey could come into play at the silicon manufacturing stage. So the silicon vendor could decide to put QuityKey in hard RTL into their device. Then the OEM chooses this device, fits their needs for everything else they're doing, plus it has SRAM PUF on it. Great. Or this OEM picks any MCU, goes through a vetting process with us, make sure that that MCU has SRAM that works, make sure that they could secure the perimeter, do all of the things that they want to do with it. We say, yes, that's a great device. You can load BroadKey on there. And again, You could skip this step and go straight into the contract manufacturing phase right here and do this with Broadkey. Not have any dependency on an NCNR product, minimum units, minimum volume, setup fees, or other things that small volume fractured IoT guys can't afford to do. So this allows those guys that want to run a 10,000 unit run on that, get right up and running. They don't have to buy 100,000 devices to get started. From here in contract manufacturing, and I will show you this process in the next slide, we go from hard IP or software IP on there. Everything gets down to a device unique certificate. That's part of what we're showing in the partnership with Global Sign here. So this could be a Global Sign signed certificate all the way down in your device at contract manufacturing. That gives the OEM then the flexibility to go out in the field and provision application keys. Those application keys push out location services or music or fund transfers, things like that. All because you can prove all the way through this chain that that smartwatch right there is still indeed that smartwatch which was built off of this device. So, IoT security landscape. That was the small stuff. That was the leaf on the tree. Now this is the forest. Okay, so we're taking a zoom all the way back up to look at why is strong device identity important inside of IoT space. So let's layer out the IoT a little bit. Things, that's how it starts. That's the T in IoT, right? You've got home automation, fitness. On the enterprise side, you've got smart meters, building access. What are the security standards over there? What are they worried about when they talk about security at this level of things? They want authentication. They're looking at biometrics. They're looking at identity. They want to prove that the device and the user are who they say they are. Then what happens is you start going up through the network layers. You go to gateways. So you've got M2M, you've got Wi-Fi, Zigbee, all of these ways that are collecting all of these nodes information, pulling them into the gateway. That's where they're worried about wireless LAN, PAN, encryption, IPsec, TLS. This gateway section here is worried about the connection up into the cloud. It's not as worried about the authentication piece. There is some authentication for these devices, but really it's trusting that that node, where it's going, that's that problem. It's the problem up here. It's not the gateway's problem. Compute and storage, which cares even less about authentication. It just wants to push big bulk data into either storage or the cloud so that you can get to it at some point. They're worried about NAT translation, port filtering, packet inspection. They're worried about the big picture of this pipe and where it's going. Where do you get back to where they care about authentication? Applications and analytics. So this is where you've got your home automation system here. This is where you're getting your home monitoring service. This is where authentication comes back in. It wants to look at this device, make sure that it has the rights and roles to be able to do these things. Secure payments, remote diagnostics, permissions control. So if you take a look at that far right side, authentication is the key that tunnels up through the gateway compute storage layer, gets up to the applications. Now it's between that application and that end thing to build its trust. And what we're talking about with device trust here is that authentication that that device is still the same device that you trusted when you first started. Take another look at this. Same layers, things, gateways, compute and storage, applications. Let's look at IoT security levels. I'm going to talk about, very quickly, security level 1.0. This is gateway PKI. So I'm skipping straight into PKI and assuming that you know what a public-private key pair and the importance of PKI. So that is a way for this gateway to trust this application. It's the way that it drills up through here. This is not even fully deployed right now, okay? And all this does is creates a connection point between the application and the gateway. Assumes then the nodes on the other side are trusted. I'm just gonna trust that since you're this gateway and you're sending me this information, you've taken care of this yourself. And we all know this isn't being taken care of in the way that we'd like to see it taken care of. Let's move to 2.0. That's where we move to the device PKI. So this is a great step, big step. It moves from just connecting the gateways to the applications to connecting the applications to the devices themselves. This is based off of an MCU with a key that's burned into OTP. So that's great. It's got a unique identity. So this is a big step, but this is only 2.0 on the security level. We believe we represent the 3.0 level, which is we've taken that unique identity, we're connecting it to the application, but we're doing it with internal root key generation, so it's not created outside. We're doing it with unclonable identities that can't be copied and pasted onto something else and have it work. We're doing it with keys that are protected on the device, more so than this level, and also deployable across any MCU. The importance of that is that you don't have to wait until you have the right MCU, the right security MCU, the right OTP, the right model, all of that stuff. Deploy now. Go out with security rather than thinking about it later or having the complications of a kind of a heavy burdened model right now. We really want to make this light and easy so that we can get down to the authentication of everything. So this is actually the demo that's running over there around the corner, and this is the last slide. If we look at an IoT device, this has broad key loaded on it. First step, the SRAM PUF generates a unique fingerprint for this device. Second step, a private and public key pair are created. The private key, only used when it needs to be used, you'll notice is not stored anywhere. It's only used in this process to get this private and public key pair established. A provisioning PC then pulls that public key out. The request goes up to the global sign high volume CA cloud service. Out of that high volume cloud service comes the device unique certificate. So this isn't a product level family certificate. This is a certificate that is unique to this specific device. Then the provisioning PC sends that unique certificate onto the device. Now you're all the way back out to where I was talking before. Once you've got that certificate, you're ready to go out in field provisioning anything that you want to do now to build up your security subsystem around that device. That, in what, 20 minutes, even under, is the overview.